In this video, we are going to talk about residues and the Cauchy residue theorem. This is our overview slide, which we'll spend about 5 minutes going over before we go over each of these topics in more detail and with more examples. The first thing we'll do is review Taylor and Laurent series. For the overview slide, I just put in the Laurent series definition here. So when z is an isolated singular point of a function f, there's a positive number r2, that's a radius, such that f is analytic at each point inside the circle of radius r2, and that is not equal to that singular point z naught. Consequently, f of z has a Laurent series representation in that circle of R2. And the Laurent series representation takes this form: f of z equals n equals 0 to infinity a n z minus z naught to the nth plus summation n equals 0 to infinity bn over z minus z naught to the n. If all the b sub n's are 0, so if this summation here is 0, then what you have is a Taylor series. And what a Taylor series allows you to do is represent a function with a polynomial. That's any function with a polynomial, so it's kind of amazing. Then what the Laurent series does is it expands the definition of a Taylor series so you can have exponents of your variable z be negative. So here you have negative exponents, but now, of course, you open yourself up to possibly having singular points where you have division by 0. Which is why you have this definition here about z naught being an isolated singular point and where it's analytic, which is in the punctured disk. Here we have our formula for the Laurent series, as well as the formula for the coefficients a sub n for the analytic portion, and then the formula for b sub n are coefficients for the principal part of our Laurent series. And I don't know if you remember this about Laurent series or noticed this about Laurent series. We never really used these formulas, these integration formulas, to get a sub n and b sub n. What we did instead is we used some of our Taylor series where we used our other formula for the a sub n, the one with the derivatives. And once we had some known Taylor series, some Maclaurin series expansions, we used our known Maclaurin series expansions to find representations for other functions. And these were the functions we used: the e to the z, the 1 over 1 minus z, the sine z, and cosine z. And we would use these basic functions, basic known functions, and replace the z with simple functions, or we'd multiply the entire equation by a value, or do term-by-term differentiation. This is how we went from sine to cosine, or we made adjustments to summation indices. And that way we found new Laurent series. So I thought it was kind of strange. We had these formulas here, which is part of our definition of the Laurent series, but we never really used these formulas until now. And actually, the way we use them, it's going to be interesting. So let's go on and review residues. So we're going to use B1. B1 is this term here. So it's the coefficient in the Laurent series that goes with the z minus z naught, where n is equal to -1. We're going to use this B1 to get a formula for the integral of f of z around c. So looking here at our formula for the coefficient b sub n, let's consider n equals 1. Then we're going to get, here we have B1, we're going to move the 2 pi I to the other side of the equation. We're going to have the integral of c of f of z, and then here, because n is equal to 1, this goes to, the exponent goes to 0, so this just becomes 1. So what we have is a formula for the integral, the closed curve integral around c of f of z dz is equal to 2 pi I times the residue, and that's what we call this B1, the residue at z equals z naught of f of z. And then the bigger theorem to go with this is Cauchy's residue theorem. Let C be a simple closed contour described in the positive orientation. So here I have a drawing of C. If a function f is analytic inside and on C except for a finite number of singular points, z sub k, and here I have z1, z2, up to zn, inside C, and these are all singularities inside C. So we don't care about any of the other singularities outside C. Then the integral, the closed curve integral over C of f of z is equal to 2 pi I times the sum of the residues of f of z. I'm going to mention this theorem here, the Cauchy-Gorsatz theorem from chapter 4. I stuck it here because I feel like it's related to Cauchy's residue theorem. So the Cauchy-Gorsatz theorem said if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. So I think of this as like the same thing as this, except now you don't have any residues because you're analytic everywhere on the circle and interior, so it's 0. Whereas the Cauchy residue theorem says you have a finite number of singular points, and so then your integral is equal to 2 pi I times the residue. When you have no residue, then the residue is equal to 0, so this whole side is 0, and you get Cauchy-Gorsatz. Or another way of looking how they're related, if you had the Cauchy-Gorsatz theorem, which was great because your integral is equal to 0 and what's easier to do to calculate, but you say, well, that's great when you have things are analytic everywhere on the closed curve and inside, but what happens when you aren't analytic inside? And the answer is you use the Cauchy residue theorem. And you can see it's also a very simple form, 2 pi I times the residue. Of course, the difficult part of this will be to calculate the residues. Well, that's it for the overview, so let's go over each topic in more detail. We are going to start with a review of the Taylor and Laurent series. So first, the Taylor series. Suppose we have a function that is analytic throughout a disk where the radius is equal to r naught. So here's my picture, here's my z naught, which is the center of my circle, and my disk are going to be all the points z, where the distance between z and z naught is less than r naught, our radius. Then f of z has the power series representation, or the Taylor series representation. F of z equals summation n equals 0 to infinity, a sub n, z minus z naught to the n. In this case, we say our series representation is centered at z naught. That is where our representation is best, has the best, actually it's like actually absolutely accurate. And then as we move away from z naught, our representation becomes a little less accurate. And this representation is good wherever we're analytic, which we determined was in this disk of radius r naught. And we had a formula for our coefficients an based on derivative. That is, it's equal to the nth derivative evaluated at z naught divided by n factorial. And Taylor series was actually really remarkable because what it tells you is any function, absolutely any function, as long as it's analytic in the disk, can be represented by a polynomial. The limitation of Taylor series, as you can see, is this polynomial has to be analytic. So what we came to was the Laurent series that says, suppose a function is analytic throughout an annular domain. So z minus z naught is between r2 and r1. And we're centered at z naught. So I've adjusted my drawing here. Here's z naught. That's going to be where we're centering our approximation. And now z naught, and we're centering at our approximation where our function may not be analytic. So this is a possible singularity. And then we said, okay, well, we'll kind of surround our singularity by a small circle of radius r1. And r1, we're going to make infinitesimally small. Then our r2 is our circle where we are analytic. So we're analytic in this yellow area between the two circles, that annular region. And the idea is we're going to shrink r1 until it only includes z naught. Then if we have C, a positively oriented simple closed contour around z naught and lying in the domain, in other words, where it's analytic, so maybe this might be C, our closed contour C now. And again, we're lying in the domain, so we're lying where we're analytic, which is this yellow portion. Then at each point in the domain, f of z, so again, we're in the domain, f of z has a Laurent series representation, and we have this formula here. F of z is equal to n equals 0 to infinity, a sub n, z minus z naught to the nth. That's the analytic portion, which is exactly the Taylor series, plus summation n equals 0 to infinity, b sub n over z minus z naught to the n. This is the principal portion. And then we have the definition of the coefficients a sub n and b sub n in terms of a integral. And as I had mentioned in our overview slide, like we never used these formulas to calculate the coefficients. What we did is we used some Taylor series expansions of different functions where we calculated those using the derivative, and we got some known Taylor series expansions and Maclaurin series expansions, which are Taylor series expansions centered at z equals 0. And then we would use those known formulas to come up with the Laurent series for other formulas. And the known formulas that we used often were e to the z equals the series z to the n over n factorial. The other formula was 1 over 1 minus z, was the series z to the n. And we had this restriction that this only converges when the modulus of z is less than 1. We had the series for sine of z is equal to negative 1 to the n, z to the 2n plus 1, all divided by 2n plus 1 factorial. And we had the series for cosine of z, which is negative 1 to the n, z to the 2 to the n, all divided by 2 to the n factorial. If we wanted then to get a series representation of e to the 1 over z, what we would do is we would look over here at our known series and look to see what it was most similar to. So it doesn't really look like this polynomial over polynomial. Could look like sine or cosine, but it looks most similar to e to the z. And what we did is then we take this formula, and there are different steps or things we can do to replace this z. The first one is replace z with a simple function of z. In this case, we replaced with 1 over z. So in the formula, we have e to the z. We replace z with 1 over z now. The summation of z to the n, which we replace with 1 over z to the n, and then we have our n factorial. So this will give us our new Laurent series. And you see we have this Maclaurin series, this Taylor series here, where we only have positive exponents of z, and we've converted it to a Laurent series where we only have negative exponents of z. And I should go back and say, for other examples, some of the other steps or techniques you might do with these 4 formulas are, in addition to replacing z with a simple function of z, like 3z or z minus 1 or I times z, we might multiply the entire equation by a value, we might do term-by-term differentiation, or we might make adjustments to summation indices. That's it for my review of Taylor and Laurent series. I do have a separate video on Taylor series. I have at least 2 other videos on Laurent series. We will do a number of examples of Laurent, but if you want more, please feel free to go back and look up the Laurent series videos I've already done. So here are a few notes on the Laurent series now, just for your reference as we continue to talk about residues. As I had mentioned for the Laurent series, we have these integration formulas to get our coefficients a sub n, b sub n, but you might recall we never used them. We did the other techniques instead. But the interesting thing is now we're going to use this formula here for b sub n, but not to calculate this coefficient, but to get a formula for the integral of f of z around the closed curve C. In particular, we're going to look at n equals 1 in our formula, and I'm just going to underline or box this formula in yellow here. So we're going to use b1 to get a formula for the integral of f of z around C. And I just actually, for easy reference, I moved this formula here. So we have b sub n is equal to 1 over 2 pi I, closed curve integral over C, f of z dz all over z minus z naught to the minus n plus 1. When n equals 1, then we get b1 is equal to 1 over 2 pi I, closed curve integral f of z dz over z minus z naught, and here our exponent will be 0, so this whole thing becomes 1, and we get b is equal to 1 over 2 pi I, integral over c f of z dz, which means that the integral now of f of z dz over c is equal to 2 pi I times b1. I am going to move my result, that formula, up here so I can continue making notes. And the first note is that b1 coefficient is called the residue. So b1 is the coefficient of 1 over z minus z naught. You can see that when we expand the summation, when n is equal to 0, we get, oh, I didn't do the 0 coefficient, but we get 1. And then when n is equal to 1, we get b1 times z minus z naught to the first power. So again, b1 is the coefficient of the 1 over z minus z naught in the expansion of the Laurent series, and it's called the residue at f at the isolated singular point z naught, and we often write b1 is equal to the residue z equals z naught of f of z. Here we have our formula for this integral when we have a single singularity at z naught. The Cauchy residue theorem allows us to calculate this closed curve integral if we have multiple singularities. So Cauchy's residue theorem says, let C be a simple closed contour described in the positive orientation. If a function f is analytic inside and on C except for a finite number of singular points inside C, then the closed curve contour integral is equal to 2 pi I times the summation of the residues. I've put a quick summary of these main points here. I have the Laurent series here, these known Laurent series, and then I have Cauchy's residue theorem. And we're ready to do our first example, which is to evaluate the closed curve integral z squared sine of 1 over z dz. The first thing to note, z squared sine of 1 over z has a singularity at z equals 0, where we have this potential division, or where we have a division by 0. So we are going to expand our Laurent series around that singularity z naught equals 0. And to get the Laurent series, what I'm going to do is compare this formula to my 4 formulas here to see what it looks most like. And the sine of 1 over z looks most like sine of z. This z squared is already in our form of z minus z naught raised to a power. So this is good. We're going to leave that alone for now, and it'll get multiplied in later, so you'll see how that works. So I'm going to leave my z squared here. My sine of 1 over z looks just like this formula for sine of z, so I can substitute 1 over z for z in this formula. So I made that note here, and I get the summation then. I replace the sine of 1 over z with summation, n equals 0 to infinity, negative 1 to the n. I have my 2n plus 1 factorial. Now this z gets replaced with 1 over z, and it's raised to the 2n plus 1. I keep my z squared, and then I plug in a few terms. Remember, I'm looking for the residue, that's b1, for my Laurent series. Plugging in n equals 0, this becomes 1 over 1, and then we have 1 over z raised to the 1, so that's 1 over z. Plugging n equals 1, we have minus, then here we have 3 factorial, and we have 1 over z cubed. Plugging in 2, we get a plus 1 over 5 factorial, and then z to the 5th, and then we'll get a minus. But I don't need to do any more, because what I see is that it is this z squared multiplied by this term here that will give me the the z to the minus 1. Remember, we're looking for, where do I have this? We're looking for the coefficient b1, which is z minus z naught. In this case, z naught is 0. We're looking for the coefficient of the 1 over z term. In this case, it's going to be minus 1 over 3 factorial, which means now my integral is going to be minus 1 over 3 factorial times my, where's my integral formula? Times 2 pi I. So my integral is equal to negative pi I divided by 3. My next example is to show that the closed curve integral of e to the 1 over z squared is equal to 0. And the first thing to notice is this e to the 1 over z squared has singularity at z naught equals 0. So we're going to expand a Laurent series around this point, around z naught equals 0. So you want to remember, you always expand your Laurent series around your singularity. Comparing this 1 over z squared to our known Laurent series, it looks like the e to the z. So substituting 1 over z squared for z into this formula here, we're going to have the summation n equals 0 to infinity. We keep our 1 over n factorial, and then instead of z to the n, we're going to have 1 over z squared to the n. And again, I notated that we're substituting 1 over z squared for z in our summation formula. Expanding this further then, just plugging in, for n equals 0, here we get 1, here we also get 1. When n equals 1, we get 1, and then we have 1 over z squared. For n equals 2, we get 1 over 2 factorial, and we have 1 over z to the 4th. Now, looking for our 1 over z term, remember our 1 over z term, that's to get our B1, our residue, we notice that there's no 1 over z term. So in other words, our residue is equal to 0, which makes our closed curve integral equals to 2 pi I times 0, which is just equal to 0. And that's exactly what we were asked to show. Our next example is to evaluate the closed curve integral 1 over z times z minus 2 to the 4th, where c is the positively oriented circle centered at 2 with a radius 1. In other words, modulus of z minus 2 is equal to 1. I drew my curve C here, so it's centered at 2 with radius 1, and then I also identified my singularities, so we have zeros at z equals 0 and z equals 2. But one thing to notice is that, well, actually, let me draw my singularities in here. I have my z equals 2, and I have z equals 0 out here as a singularity. But you'll notice it's outside my circle. So when you read the Cauchy Residue Theorem, let C be a simple closed contour, positive orientation. If F is analytic inside and on C except for a finite number of singular points inside C. So we're looking at singular points inside C. So actually we don't really care about this Z equals 0 when we plug it into this residue formula. So this here is the first important point of this example. What we're going to do then, we're going to expand a Laurent series around z naught equals 2, this singularity here inside our circle. In a neighborhood, then z minus z naught is less than 2 and greater than 0. Now this is getting a little bit detailed, but one day someone's going to ask you for details. So first, remember this neighborhood, that's not this curve C that I drew. The neighborhood, I said my radius for my neighborhood is equal to 2. So I'm going to draw that here. And it's less than 2, not less than or equal to 2, which is why I have the disk, not this circle. And what I'm saying is that my Laurent series expansion is centered at my z naught equals 2, and it's good in this neighborhood. So it's good wherever z, the distance between z and my 2, is greater than 0. So this is a punctured neighborhood. In other words, I'm not including z, because f is not analytic at z. But I am including everything in this disk, this punctured disk, that does not include the point z equals 2. So this is where we're analytic. And again, I didn't include my other point 0, which is why I made z minus z naught is less than 2. So I wouldn't eclipse 2. So again, this is my radius of my neighborhood. This 0 is what makes this a punctured disk. And just looking at this, what I've just written, and comparing it to the Laurent series expansion definition, we're saying when z naught is an isolated singular point, in this case z naught is equal to 2, then we say there's a positive number r2, and in this case my r2 is radius equals 2, so this is r2 equals 2, my radius of 2, such that f is analytic at each point z for which the distance between z and z naught is greater than 0 and less than r2. So it's this point, everything in the yellow, not including 2. Consequently, f of z has a Laurent series representation. So we're using this neighborhood to do our Laurent series expansion around z naught equals 2. These are the words you want to be able to write. This is the picture you want to keep in mind. We have our curve C that is inside the neighborhood where our function is analytic. I moved up this thing about z naught being outside of C over here, and I then talked about expanding my Laurent series around z naught equals 2 in a neighborhood over here so that we could make more space. To center at z naught equals 2, I need my expansion to be of the form z minus 2. Looking at my function, this here, the z minus 2 raised to the 4th, that's good. But I need to change this z so I have z minus 2. If I replace this z with z minus 2, I'm going to have to add 2, just so I'm algebraically equivalent, and I'm still multiplying by my z minus 2 raised to the 4th. And again, this 1 over z minus 2 to the 4th, that's perfectly in my expansion form. I want z minus my singularity, and then I can raise it to any power. So this is good. I don't have to do anything more with this. Over here, I need to do something with this to make it look more like one of these 4 forms. It doesn't look like an e to the z. It doesn't look like a sine or cosine. It does sort of look like this because I have a polynomial over a polynomial. I'm going to move this formula down here so it's closer for my reference. So if I want to use this formula, remember later I'm going to replace this z with some simple function of z. Z minus 2, that's a simple function of z, so that looks good. But the thing is I need to combine it with a plus or minus 1 out here. It can't be just some arbitrary constant. It needs to be 1. So what I'm going to do is factor out a factor of 2 from my denominator. And what I'm going to get then is 1/2 times 1 plus my z minus 2 over 2. And again, if you multiply this by 2, you'll see you get this denominator here. So we're good algebraically. We still need to multiply by 1 over z minus 2 raised to the 4th. And the next thing I want to do, because this is a minus z, I want to make this negative. So I'm going to put a negative out here, which then I have to introduce another negative. So minus z minus 2 over 2 times my 1 over z minus 2 to the 4th. And now I can use my formula, and I'm going to substitute minus z minus 2 over 2 for z in this formula. So what I get, I have my 1/2, and then over here, remember this part here is going to substitute for this z. So I'm going to have my summation of minus 1 to the n, that's this negative 1 here, z minus 2 over 2 to the n. And then I also need to multiply by 1 over z minus 2 to the 4th, which I put out in front of the summation. I moved this 1/2 to combine it with the 1/2 here in my summation, so I still have my 1 over z minus 2 to the 4th summation minus 1 to the n. Now I have 1/2 to the n plus 1, again combining this 1/2 to the n with this 1/2, and then I have z minus 2 to the n. Now from here, what I want to look for is for the residue, which is the b1, the coefficient the coefficient of the z minus 2 to the negative 1 power. So looking over here, this is where I have my negative exponent, and I'm going to be multiplying by this positive exponent. So when n is equal to 3, that's when I'm going to get the z minus 2 to the minus 1. I note that my b1 is going to come when n is equal to 3, and my coefficient, when I multiply this out, is going to be negative 1 to the 3rd times 1/2 to the 4th. That's this term here. So my B1, my residue, is equal to minus 1/16, which then implies my closed curve integral of 1 over z, z minus 2 to the 4th, is equal to 2 pi I times minus 1/16, which is equal to minus pi I over 8. A couple of last comments about this example. So the things I think is interesting is we do have this singularity, z equals 0, that's outside of C, so we just ignore it. And then the other thing I thought was interesting is this z, then we need to center it at z equals 2, and we did that just by introducing a minus 2 in the denominator, but we also had to add it back. And then we have the Cauchy Residue Theorem, which we already talked about, but I'm just going to read it just because. So let C be a simple closed contour described in the positive orientation. If a function f is analytic inside and on C except for a finite number of singular points inside C, then the closed curve integral along C of f of z is equal to 2 pi I times the sum of the residues for the singular points that are inside C. So this is our example where we have more than one singular point inside C. So the example is to evaluate the closed curve integral of 5z minus 2 divided by z times z minus 1, where C is the unit circle, absolute value of z is less than 2. And the first things I like to do is graph my C. This is important so you can see which residues or which singularities are inside C and which are not, and then also point out my singularities. So here's my graph of C. It's the unit circle centered at 0, radius 2, and my function 5z minus 2 over z times z minus 1 has singularities at z equals 0 and z equals 1. So we will need a series to be centered at z equals 0, where then we'll find our residue for z equals 0, but then we'll also need to do another series, a second series at z equals 1 to find our residue for z equals 1. We are going to start with our Maclaurin series centered at z equals 0 with radius 1, and our radius has to be 1 because we don't want to hit this other singularity at z equals 1. So our distance between z and 0 needs to be less than 1, which is why our line is dotted. When we're centered at z equals 0, this z is good. This z is good too because it's sort of in this type of form. We might need to introduce a negative sign though. This z looks good. We have this minus 2, but you know what? We can separate out these two fractions so that we have 5z over z times z minus 1, minus 2 over z times z minus 1. Here the z's cancel out. We have 5 times 1 over z minus 1, and then we have 2z times 2 over z minus 1. So now everything looks to be either in this form or centered at 0. I'm going to bring down this formula here of our known Laurent series over here just for easier reference. And the first thing, comparing these fractions to the 1 over 1 minus z, this fraction and this fraction, they're both almost what I want, but I need the one to be positive, so I need to introduce a negative sign. And that's what I've done in this step. So I have a negative 5 now, 1 over 1 minus z. Here this negative becomes positive 2 over z times 1 over 1 minus z. Using this formula now, because I have exactly this form, I can substitute for 1 over 1 minus z this summation z to the n. So I have negative 5 times summation n equals 0 to infinity z to the n, plus 2 over z summation n equals 0 to infinity z to the n. Writing the first few terms because I'm looking for b1. So I have my negative 5, my z to the n is 1 plus z squared, and then my 2 over z, 1 plus z squared. Looking over here, 5 times all of these terms, I'm not going to get any negative exponents, so this is not going to help me with my b1. Here I have 2 over z times 1, that's definitely a z to the negative 1, or z minus z naught being 0, to the negative 1. So this is going to contribute to b1. Here, I'm going to start getting positive exponents again, which means the only thing contributing to B1 is 2 times 1 over z. So B1 is equal to, and that's at z equals 0. I want to remember for which singularity this residue is. So B1 for z equals 0 is equal to 2. In our previous example, then we just multiplied B1 times 2 pi I, but we can't do that in this example because we have more than one singularity. Now we need to figure out the residue for z equals 1. But first, I'm just going to make my notes for the singularity at z equals 0. This is when we had this circle centered at z equals 0 of radius 1, and our residue is equal to 2. And now I'm ready to look at my singularity, z equals 1. I'm going to center a Laurent series expansion at z equals 1. Here I am at z equals 1. And I want the distance between z and my 1 to be less than 1. And I want it to be greater than 0. So in other words, I'm looking at this disk in green. It's less than 1 because I don't want to include my z equals 0. So my disk, my radius needs to be less than 1. And again, it needs to be greater than 0 because I want the punctured disk that does not include this middle here. So centering at z equals 1, in other words, the form of my expansion is going to look like z minus 1. When I look over here, I need to see, what do I have? Well, this z minus 1 is in the correct form. This is almost in the correct form, aside from these coefficients are wrong. And this is not in the correct form. I'll need to add a minus 1, which means somewhere along the line I'll need to add a 1 to my factor here. The first thing I did is I worked on my numerator. I converted this z to z minus 1. And in effect, what that did is it gave me another term of minus 5. So I'll need to add 5 back in order to be algebraically equivalent. So that's the numerator. Looking at the denominator, z minus 1 is in the correct form, but I wanted to get this z in the form of z minus 1, which I did right here. But in order to do that, I need to add back 1. And again, this whole factor here needs to be multiplied by z minus 1. I did the algebraic simplifications here. I still have 5z minus 1. This becomes a 3. And then over here, what I did is I took my z minus 1 and grouped it with my 5z minus 1 plus 3. And then I multiplied this whole thing times this term here. So again, this became just something, another factor now. This was kind of nice. These canceled out. So what I get is 5 plus 3 over z minus 1. And then this factor here stays the same. Oh, wait, no, I did one thing. Because I'm going to be using this formula, I introduced a negative sign here, which converted this to 1 minus z. Now, using this formula, which I rewrote here, what I did is I substituted this 1 minus z in for z. So I still have my factor of 5 plus 3 over z minus 1. Then this factor becomes my summation then of 1 minus z to the n. And also remember, when we used to use this formula, we would verify that the absolute value of our simple function of z is less than 1. And I did that here, but that just comes from the condition of our domain. So we're good there. Moving on with more algebra, then I plug in n equals 0, and that will give me this raised to the 0 is just 1. When n equals 1, I get 1 minus z. When n equals 2, I get 1 minus z squared. And I just realized when I was doing all my algebraic manipulation, I had converted my z minus 1, which is my z minus z naught, to 1 minus z, which is a problem now because I can't combine this 1 minus z and cancel out with this z minus 1. So I'm going to need to redo this. I'm going to need to throw in like another couple of negative signs. So again, hopefully you see that problem. When I had converted this, I had moved away from z minus z naught, and I get z naught minus z, which isn't what we wanted. Like, it doesn't work here. As I mentioned, the solution is more negative side, so I'm going to multiply by -1, and then multiply my 1 minus z by -1 to get z minus 1. And now I'm going to be substituting my -1 z minus 1 for z in this formula here, the 1 over 1 minus z equals summation z to the n. That will give me my 5 plus 3 over z minus 1 times summation -1 to the n, and then my z minus 1 to the n. When I plug in to my summation formula n equals 0, I get 1. For n equals 1, I have my -1, z minus 1 to the 1. For n equals 2, I'll get a positive z minus 1 squared. For n equals 3, I'd get a negative z minus 1 cubed, and I continue. But I can see here, when I'm looking for my b1, that's the coefficient in front of my z minus 1 to the -1 term, when I multiply 5 times this factor here, I'm not going to get anything with a negative exponent, so that isn't going to contribute to b1. When I multiply 3 times my 1, oh, that gives me something with z minus 1 to the -1. When I multiply 3 times any of these others, here they'll cancel out, here I'll get positive. So the only term that contributes to my b1 or factors will be my 3 over z minus 1 times 1. That gives me a coefficient of 3, which means my b1 for my singularity at z naught equals 1 is equal to 3. Now I've calculated that my two residues. For the singularity z equals 0, the residue is 2. For the singularity at z equals 1, my residue is equal to 3. So by Cauchy's residue theorem, both of these singularities are inside my curve C, and therefore the closed curve integral will be equal to 2 pi I times 2 plus 3, which is equal to 10 pi I. I'm ready to review what we've covered in this video. After the review, I do have one more problem for you to try. So what we've covered is we reviewed the Taylor and Laurent series. Here is what we have for Laurent series. When z naught is an isolated singular point of a function f, there's a positive number r2, that's a radius, such that f is analytic at each point z, where the distance between z and z naught is less than the radius r2 and is greater than 0. In other words, our z is not equal to z naught. Otherwise, z could equal 0. Consequently, f of z has a Laurent series representation given by this formula. F of z is equal to summation n equals 0 to infinity, a n z minus z naught to the n, plus n equals 0 to infinity, bn over z minus z naught to the nth power. This part here is called the analytic portion of our Laurent series. This part here is called the principal portion. And we have these two formulas here to calculate a sub n, the coefficients of the analytic portion, and b sub n, the coefficients of the principal portion. Generally, when we compute Laurent series, we actually don't use these two formulas, but we go to known Taylor series and we modify them so to get our Laurent series, and we've seen several examples of that. But we are going to use this formula here now to calculate a formula for the closed curve integral of f of z. And we come up with the definition of residues, and we consider n equals 1 in our formula for b sub n. So when n is equal to 1, we can multiply both sides equation by 2 pi I, so we get 2 pi I b1 is equal to the closed curve integral of f of z dz, and now the exponent over here is going to be minus 1 plus 1, so this just becomes a 1. So what this implies is our closed curve integral of f of z dz is equal to 2 pi I, and we call this b1, this coefficient that goes with the 1 over z minus z naught term, the residue at z equals z naught. To sort of generalize this result to multiple singularities, we have Cauchy's residue theorem. Let C be a simple closed contour described in the positive orientation. If a function f is analytic inside and on C, except for a finite number of singular points inside C, then our closed curve integral is equal to 2 pi I times the sum of the residues for those singular points inside C. As I mentioned, for review, I have this problem here for you to try. So pause the video, give the problem a try, come back, and then I'll have a solution for you. Here is the solution. A couple of things to note. First, I drew my circle. I identified my singularity at z equals 1, which is inside my circle. So I'm going to center my Laurent series expansion at z naught equals 1. So the denominator here is in good form, z minus z naught, z minus 1 squared. It's this z up here, that's the exponent for e, that needs to be worked on. In particular, I want to make this z into a z minus 1, but that means since I'm essentially adding 1 to the exponent, I need to subtract 1 to the exponent. Algebraically, this subtraction is the same thing as multiplying by e to the minus 1, which gives us an e in the denominator. So we have 1 over e z minus 1 squared times e to the minus z minus 1. So now I've converted all my z's so I can do a series centered at 1. This factor here looks good. It's exactly in the form that I want. This e to the minus z minus 1, I use this formula here. Our e to the z is summation z to the n over n factorial, which I moved here. And I'm going to then substitute my minus z minus 1 for z in this formula, which is what I did here. So I get a minus 1 to the n, and then my z minus 1 to the n over n factorial. I expand out this summation here, and I'm looking for where I'm going to have my b1, which is the coefficient in front of the 1 over z minus 1 term. And that would be, let's see, when I multiply this, I still have my minus 2 as my exponent. Here is where I'm going to get my minus 1 exponent. So my b1, my residue, is the coefficient minus 1 over e, which means my closed curve integral is equal to my minus 1 over e times 2 pi I, and this is my final answer. So that's it for this video. Thank you for watching.